In this work, they are described in case study section. The proposed approach for GP also uses the technique of selection by elitism. In this approach, only the individual having the best fitness function value is selected. With this, we guarantee that the results of the GP approach will always have a progressive increase at each generation. In order to find the LRM that best fits to the data obtained with communication graphs, the crossover and mutation operators are applied to the genetic individuals, the LRM trees, as shown in. The crossover and mutation operators, in genetic programming, are similar to those present in conventional genetic algorithms. Expression trees representing LRMs under the operations of A. Crossover and B. Mutation. In the first operator, represented in A, the candidates are selected for reproduction according to their fitness. Fittest candidates have higher probabilities of being selected, and, next, exchange their genetic content, subtrees, randomly chosen, between each other. B illustrates the crossover of the parents y equals beta 0 plus beta 1 dot x1 plus beta 2 dot x2 plus beta 3 dot z and y equals beta 0 plus beta 1 dot x1 plus beta 2 dot x4 plus beta 3 dot x5, generating the children y equals beta 0 plus beta 1 dot x1 plus beta 2 dot x2 plus beta 3 dot x4 plus beta 4 dot x5 and y equals beta 0 plus beta 1 dot x1 plus beta 2 dot x3. With mutation, represented in B, after a crossover operation, it is randomly generated a mutation factor for each new genetic individual. If the mutation factor exceeds a predetermined boundary, a subtree is selected at random in the LRM and mutated to a new different subtree. Illustrates the mutation of the model y equals beta 0 plus beta 1 dot x1 plus beta 2 dot zeta y equals beta 0 plus beta 1 dot x2 plus beta 2 dot x3, where it can be noticed that there was a mutation in the genetic content x1 to x2. In the approach proposed in this work, we use the two-point crossover operator, because this way it combines the largest number of chromosomal schemes and, consequently, increases the performance of the technique. On the other hand, for mutation, we use the simple operator, because the mutation prevents the stagnation of the search with low mutation factor, but if this rate is too high, the search becomes excessively random, because the highest its value is, larger is the substituted part of the population, which may lead to the loss of highly qualified structures. Once an iteration of the proposed GP algorithm is ended, the best solution found in the iteration is formally evaluated. In linear regression, assumptions about the fitted model must be considered so that the results can be reliable. So, the evaluation process consists in verifying, by residual inference, the assumptions of normality, homoscedasticity and independence about the distribution of errors of the fitted LRM. We use the following adherence tests. Shapiro-Wilk to check the assumption of normality. Broish-Pagan to check the assumption homoscedasticity. And Durbin-Watson to check the independence, absence of autocorrelation, among the errors. If the result of any of these tests is not positive and the maximum number of iterations was not reached, the GP algorithm will start a new evolution iteration through the generation of a new starting population and will follow the flow presented in. Otherwise, the algorithm presents the LRM as final solution. At the end of all the iterations, if no genetic individual is approved in the formal evaluations, the GP algorithm will select the solution with the best AIC for residual analysis. The residual analysis allows the evaluation of the assumptions about a model. So, in this work, the residual analysis is divided in two stages. Residual diagnostic plots, where we build the following diagrams. Diagram of distribution of accumulated errors, to quantify the distance between the estimates given by the LRM and the data of the training set. QQ plots and histograms, to check the assumptions about the error probability distributions. Diagram of residuals dispersion against the fitted values, to check the assumption of homoscedasticity. Diagram of dispersion of the residuals, to check the absence of autocorrelation among the errors. Application of the statistical test of Mann-Whitney-Wilcoxon to the data of the training set and the respective estimates given by the LRM found. The Mann-Whitney-Wilcoxon test is a nonparametric statistical hypothesis test used to check whether the data of two independent sets tend to be equal, null hypothesis, or different, alternative hypothesis. With these same sets, We still perform the computation of the global mean errors, as a measurement for the central location of the set of residuals, maximums and minimums. These measurements are used to check the precision of the estimates and the possibility of presence of outliers.